Assalamu alaikum. Today, inshallah, we're going to start talking about chapter 2. So without any further ado, let's start. At the beginning, as we are used to, we have to define some terminologies that we're going to use throughout the chapter. So the first term we're going to introduce is sample space. What is a sample space? A sample space, which is denoted by the letter S, is the set of all possible outcomes of a random experiment. What is a random experiment? I should have defined this first, but anyway, a random experiment is an experiment that is done in the same way, in the same process, within the same steps. However, it yields different results each time. What is an example of this? An example of this might be rolling a dice, throwing a coin, picking a random cube from a bag. All of these are considered to be random experiments. And the sample space for rolling the dice, for example, is all the possible outcomes that would come from rolling the dice, which is either you're going to get a 1, you're going to get a 2, 3, 4, up to 6. So this is the sample space and the random experiment. However, sample spaces come in two ways, either discrete or continuous. Discrete means that you can count it. You can count the number of outcomes individually. So and they can be finite or infinite. So you might have an infinite set that does not end, but however you can count each and every outcome in the set of the sample space. However, continuous, you cannot really count them. So let's say they can usually consist of intervals of real numbers. So let's say that we have an interval from 3 to 5. You cannot count the numbers, all of the numbers between 3 and 5. They are infinite number of numbers. So you might have 3.000001 or 00002, and as you go. So this is it for the sample space. Now let's see some examples for how the sample spaces are written. So let's say we have a random experiment of tossing the coin once. So if we toss the coin once, what are we expecting? What are the results that we are expecting? We're expecting either to get a head or a tail. So the sample space would look like this. It is a set. So we're going to have it written as a set, and this is our first outcome, and this is our second outcome. Bear in mind that I have highlighted the word once here, because if you toss the coin twice or thrice or multiple times, you're going to have different sample spaces, and we're going to see them. Now let's have a different experiment here. Let's say that we have a bag, and this bag has cubes in it. Each cube is a different color. So our random experiment is reaching inside the bag and pulling out a cube from the bag. So what are the possible outcomes? Let's say that we have 4 cubes. Each cube is a different color. Let's say it's red, green, blue, and yellow. So what is the sample space for the random experiment of pulling a cube from the bag? We're going to have a sample space that looks like this. So R denotes the red cube, green denotes the red cube, and so on. Now let's see if we toss the coin 2 times this time. How is our sample space going to change, since we're only going to get either a head or a tail? Well, we're going to get a sample space that looks like this, where it takes into consideration the number of times you have done the random experiment, or how you define your random experiment. If your random experiment is defined as tossing the coin twice, your sample space should include the 2 times you have tossed the coin in each of these outcomes. So it would look something like this. So let's say you may toss the coin, you get a tail, then you get a head. So it's included here. Or the first time you toss, you get a head, and then you got a tail. So it's included in here, and so on. And here is also a sample space for when you toss the coin 3 times. Now let's have some practice about these sample spaces. We may get some questions in the book about finding sample space for other random experiments. So let's see how can we find them. So the question says, find the sample space for each question below. We have 2 questions. First question says, each of 3 machine parts is classified as either above or below the target's specifications for the part. It's kind of a story, but what we need and what we have to understand from this question is that they have a classification where they have 3 parts, and these 3 parts can either be above or below the classification. So first we have to denote our classifications. We have either above, which we denoted by the letter A, as we did to the head and tail, the tossing the coin. We denoted the tail with T and the head with H. So we denoted the above classification with A and below with B. Now, it says that we have 3 machine parts. So what are the possible outcomes that gonna get from such a random experiment? So for example, let's say that the first machine is above classification, the second one is above, and the last one is below, or all of them above, or all of them below, or the first 2 are above and the last one is, you get it, you get the idea. So we're gonna end up with a sample space that looks like this. It's a set and it includes all the possible outcomes. So going to the other question, the other question says each of 4 transmitted bits is classified as either in error or not in error. So as we did here, we have to denote our classifications here. So we denote this the error in E with the letter E, and we denote the not in error as O. And we have 4 transmitted bits. So the possible outcomes of having this random experiment is, for example, let's say that all of them are in error, or all of them are not in error, or the first 2 in error, and you get the idea. We're going to end up with a sample space that looks like this, where it includes all the possibilities of this random experiment. So let's say that you may find some difficulties in solving some sample spaces. Maybe they are difficult, or you just want to make sure you have much time in the exam and you want to make sure of your answers. So a tree diagram may be useful for you. Tree diagram is not a foreign concept. We've seen these shapes before in middle school and even in high school. So let's say we have this example. The example says messages are classified as on time or late. So classify the next 3 messages. So we have 3 messages and we want to classify them as either on time or late. So let's start with the first message here in the tree diagram. So we know the messages come either on time or late. So it's gonna have 2 branches, on time and late. So let's say we follow one of them, and we're gonna do the same thing we do here to the other side. So let's say this one on time. So we have this next message, and the next message is also either on time or late. So we go to the next message. It's either on time and late, and you get the idea. You can do it, and if you want to read the tree diagram, so you either read it from below to top, or from top to below. Don't stay consistent with one of them. So because if you read half of them up from top to below and the other half from below to top, you're gonna get a different result. You're gonna get I think a wrong answer, because I've tried it and it did not work for me. So this is a sample space for this example. So let's talk about events now. What are events? Events are just subsets of the sample space. So we have a sample space and we're taking subsets, some outcomes from the sample space, and we are assigning them a variable, and we're calling them events. So we have our sample space here for tossing the coin 2 times, and we have, let's say that we have event 1 and we assign it, the double T. You can assign it as anything you want. Like for example here, E2, we assigned it these 2 outcomes, and E3 we had these outcomes in it. You can do whatever you want. Like you can assign it whatever is inside the sample space. Now, these events have operations that you can do on them. So we call them event combinations, and there are 3. The first one is a union, second one is intersection, and the third one is a complement. A union is a grouping of 2 events. So let's say we have this event and this event. A union between them is a set that includes the outcomes here and the outcomes here together. So this is a union, and it is inferred in written questions, usually, not always, but usually it is inferred by the word or. So if you see the word or, that might infer that you have a union here or something of that sort. So keep an eye for it. It is denoted by this U-shaped between them. We have also, as I said, intersection, and intersection is the commonality between 2 events. So let's say we have event 2 and event 3, and we want to find the intersection between them. So the intersection between them is all the outcomes that are in event 2 and also in event 3 at the same time. So in this case, the intersection between them is going to be the set that includes TH, since it's in both, and HT, also in both. So this is intersection, and it is denoted by this N shape, this shape here. And it is inferred in written words by and, usually. Last one we have is the complement of an event, and the complement of an event is all the outcomes that are in the sample space but not in the event. How? So let's say we want to find the complement of E1 here. So finding the complement of E1 is looking at the outcomes that are in the sample space that are not here. So here we have double T. So the complement is going to be everything in the sample space except for double T. So this is the complement. It is denoted by this dash here, or prime. We call it a complement, and in written words inferred as not. Now, let's talk about discrete events. Let's have a question about them. The question says, solve the question below for the events of tossing the coin twice. So we have these events here of tossing the coin twice, and we have some operations that we have to do on these events. So let's start with the first one. The first one says a union between E1 and E2, which should be a set that includes whatever in E1 in addition to whatever in E2. So this set would look something like this, where it has TT, TH, and HT, like there. Now the intersection between E3 and E2. So let's find the common things. As we said, the intersection is the common things. Let's find the common things between these two. So it is TH common between them and HT also common between them. So it should look something like this. Now let's find something, now the second one is finding the intersection between E1 and E3. Let's see the common things between E1 and E3. So E1 have double T and E3 has these outcomes. As we can see, there is nothing between them, nothing in common. So what do? We say that it is an empty set. The intersection between E1 and E3 is an empty set, and we denote it by phi, the Greek letter phi. Now, let's find this, and let's find the set for this question here, which tells you to find the union between E1 and E3. So E1 here and E3 here. So if we find the union between them, we're gonna have all the possible outcomes. What is this? This is our sample space. So the union between E1 and E3 is our sample space, which is including all the possible values in the sample space. And the complement of E1, as we saw previously, is all the outcomes that is inside the sample space that are not inside of here. So it would look something like this. Now let's solve a question on continuous events. So the question says a measurement of a thickness of a part are modeled with a sample space of S equals R positive. So as we have said, continuous sample spaces are intervals, not necessarily a number of outcomes that we can count. They are just intervals of real numbers. So our sample space is an interval from 0 up to infinity, where it includes all the positive numbers. Now, the events are going to be also intervals, since the sample space is intervals. So our events going to look something like this. We have these events, and we have to solve these questions on these events. So let's start solving them. Extremely easy, like the discrete ones. So the first question says a union between event 1 and event 2. So we have to extend. We have here two intervals, and we have to extend these two intervals based on the interval they are being grouped with. So we're going to end up with something that looks like this. From 10, lowest value here, to 15, the highest value here, and everything in the middle is filled with the already existing interval here. So now let's go to the other one. Event 1 intersection event 2. So we have to find the common ground here. So what are the numbers that are inside here and also at the same time are inside here? If we do it, I should have done a number line on this question, but I forgot. So if we do it, and if we draw a number line and see, we're going to have this interval here. Now, let's take the complement of event 1. We can take complements on continuous events. So what is the complement? The complement, as we have mentioned before, are all the outcomes that are not in the event, but are in the sample space. So our sample space, as we said, from 0 to infinity. And our event 1 that we're going to find the complement for, is from 10 to 12. So we have all the numbers from 0 to infinity except the numbers from 10 to 12. The answer would look something like this, but you have to bear in mind that if you're finding the complement of a continuous event and you have an equal here, the equal is not gonna be here. And if you don't have an equal here, the equal is gonna appear. So keep this in mind. Now, the last one here, it wants you to find the intersection between the complement of event 1, the one we have just found, and event 2. If you do it, you're going to find it to be this one here. Here is a question in the book if you would like to do more practice. Now, let's talk about Venn diagrams. Venn diagrams are these circles that we know from middle school. So let's talk further about them. So each circle in this Venn diagram is an event. And the square, you see the square that include the both circles, is the sample space. So all of this, everything inside of the square is in the sample space. And everything inside the circle is in the event. So event A has this circle and event B has this circle. We can see operations done on the Venn diagram. So as we can see here, the union between event A and B looks something like this, where the shaded area is the subset that we are taking from the sample space. And the intersection between them is this small area here. And we can have more complicated ones, one that looks like this and the other that looks like this. So let's talk a little bit about mutual exclusivity here. Mutual exclusivity are when events don't share any commonalities, and we can see them. The occurrence of one of the events tells you that the other did not happen naturally. So it symbolically shows something like this. Remember the phi, this is the mutual exclusivity sign, where the two events have no intersection between them. We call them mutually exclusive. And it is, if we would like to show it on a Venn diagram, it looks something like this. There is no common ground between this event and this event at all. So, mutual exclusivity laws. So there are some laws that include mutual exclusive events that you can do on them and are special for them. So the first one is the commutative law. By the way, these laws, the first three laws that we're going to be talking about, are the same one, like the same ones we had in algebra. So if you remember the names in algebra, they are going to be applying also to these operations here. So the commutative law, where order does not matter, so you can take the union, the intersection between A and B and A, or union between A and B, and it does not matter. If they are mutually exclusive, you can do this guilt-free. The second one is distributive, where you can you have an argument inside of a bracket, and you can expand it by doing the operation outside on them and then joining them like this. So if I'm going to explain it, it's going to be just more confusing. So look at the picture and you're going to understand it. It's extremely easy. You can imagine that this is addition here and this is multiplication here, and you can get an idea on how this happens here. So we have associative law, where as we have said, the commutative, the difference of flipping the operation does not matter, and also doing the operations in any order also does not matter. So this is for the associative law. Now we're going to get to the new ones. The first one is De Morgan's law, which we're going to use in some questions. So it's important that you write it down or keep it close, because it's going to be handy. And it is kind of confusing to explain, so just look at on how it's represented here, and we're going to solve question on it so we would know how to use it. So it's something like this. And we have the complement law, which is self-explanatory. The complement of a complement of event is the event itself. Looks something like this. Now let's have a practice on the Venn diagram. So let's say that we have this Venn diagram here, where we have three events, A, B, and C, each denoted by a circle by itself, and the sample space is the square, including all the circles. Let's solve these questions. So, first question is the complement of A. We know the complement of an event is all the events in the sample space that are not inside the event. So, event A is this circle. So, the complement of it is everything except this circle. So, shade everything except this circle here. Now, the intersection between A and B. So it's the area that is common between A and B. So it's going to be this small area here, this area between A and B. So it's going to be something like this area shaded here. Now, a question C. It wants the intersection of A and B first, then it wants the union of C. So what's going to look like? We found this one here. It is this area here, and then we add just the circle C to them, and it's going to look something like this. Question D, the union between B and C, that's circle B, that's circle C, and then you get the complement. So after you get the union between them, it is going to be both of these circles shaded. So then you get the complement, then you shade everything except for these two circles. It's going to look something like this. And the last one here is finding the intersection between A and B, which we have already found about 3 times now, which is this small area here. And you get the complement. So it means that you shade everything except this small area. Then you add this small circle here, which gonna look something like this. Now, counting techniques. We finished with the very easy part. Now we get to the kind of complicated part of the chapter. It's not that complicated. It's just confusing because there are a lot of things to take in. But once you get them all down, they're gonna look extremely silly and extremely simple. So counting techniques are the rules to determine the number of outcomes. We have seen simple outcomes yet, like outcomes when you're rolling a dice. You can count the number of outcomes yourself. However, let's say we have a really complex random experiment or a really complex event, and we want to find the number of outcomes for it. We're going to use one of these 3 counting techniques. The first one and easiest one is the multiplication rule. And the second one is the permutation rule, and the third one is the combination rule. These 2 people often confuse them together all the time, so you just need to practice them more so you can get a better feeling for them. And you make sure that you always use the correct tool for the right job, because if you need to use multiplication and you use one of these 2, you're gonna get a totally different result in a totally different dimension. So yeah, let's talk about multiplication rule. Multiplication rule takes into consideration the number of options you have in each step. Of course, you're not going to understand it from just plain text. We have to have an example, and we're going to have an example. This is the formula for it, where you multiply all of the options with in each step. And an example of this might be, let's say we are designing a website. So we have a website and we want to design it, and we have options on on the things we can include in this website. So let's say we have 4 theme colors, 3 fonts, font means khat, or 3 layouts, and 3 layouts. So we have all these options. So how can we find the number of possible outcomes or combination or mixing of these together? The way to do it is extremely easy. As we see here in the formula, we multiply the number of options of each step with the number of options in the other step, and so on. So it's going to look something like this, where we use multiplication rule, and the first option and the first step, we have the theme color. We multiply the number of options in it with the next step, which is the font color and the layout, and we multiply it together, and we get the number of possible designs or possible outcomes, which is 36. Let's get in other examples. Doesn't hurt. So we have these 2 examples, which look like stories, which is something more of the questions of the book. It's also going to be a story. So you have to get yourself familiar with reading these stories and get what you want from these stories. So the question says, in a manufacturing operation, a part is produced by machining, polishing, and painting. If there are 3 machine tools, 4 polishing tools, 3 painting tools, how many different routings for a part are possible? So we can see that we have here 3 steps. The 3 steps are machining, polishing, and painting. And for each of these steps, there are different number of options here. So in the machining step, we have 3 tools we can do the machining with, 3 options, and 4 for the polishing and 3 for the painting. So if we write them here, we can see clearly that we might need to find we will use the multiplication rule to find the number of possible routings that we're gonna use, because we have options and we have steps, and at each step we have a number of options. So we multiply them together and we get this number, the number of possible routes a part can take. Let's go to the other question. The other question says, a new design for a wastewater treatment tank have proposed 3 possible shapes. Have proposed 3 possible shapes, 4 possible sizes, and 3 locations for input valves and 4 locations for output valves. How many different product designs are possible? So here we have various options. So we have possible shapes. We have first step, which is shapes. We have sizes. We have the location for input values and location for output values. So here we can clearly see that we can use multiplication rule to get the number of different product designs possible. So we write them here for the sake of clarification, all of the possible ones. Then we multiply them with each other. We get the number of possible product design in this case. Now we talk about combination. Combination is a selection of R items from a set of N. So R is the number of items you're gonna select, while N is all the items in the set that you're selecting from. And it's highlighted here in red that order does not matter. And we're gonna explain when order matters and when does not matter and how does it matter and how does it not. This is the formula for combination. We have only one formula for combination. And yeah, that's it. As we can see here, N is the number of items we have in the set. So maybe you have a set of 140 products, for example. We want to choose 5 from them. So the 5 is denote the R, the numbers that we want to choose. This argument here is sometimes read as R choose N, I think, or N choose R. It has choose in it. So you're going to be choosing from it or something like this. Now let's talk about order. Now this cute example of candy. So let's say we have 10 candies. Each and every single one of these candies is perfectly similar. They are exactly the same. There is no distinction between them. There is nothing different between them. So the question says, do we really need to think of them, each and every one of these candy, to think of it as to think of choosing one over the other, or choosing this one first or the second one first, or this one to be chosen first? Does it really matter? Because since they are the same, well, in the case of the combination, it does not care. The combination simply does not care if you choose the first candy before the seventh candy. All it cares about that, okay, I'm gonna include the case where you include the 1 and the 7. Either the 1 was first, the 7 was first, I don't care. As long as they are together, I'm gonna count them as one outcome. So we can see here where order matters. If you classify candy number 1 and 2 and 3, if you take them, if order matters to us, if you take candy number 2 before candy number 1, it's gonna be a totally different outcome in the case of the permutation, or when order matters. But in the case of where order does not matter, in combination does not care about order. So all of these sum up to be just one outcome. While here we have 6 distinct different outcomes, here we consider it just to be one outcome, and we don't care because they are all the same, and there is not going to be anything drastic if we chose 2 before 1 or 1 before 2. As long as they are grouped together, that's what we care about. Now let's practice combination. And excuse me if I got out of character, because these questions, they require it. So the question, of course, is going to be a story. So the story says, a batch of 140 semiconductor chips is inspected by choosing a sample of 5. So first of all, we know that our set, our N, is 140. This is our bigger set. And we are choosing 5 chips from it. So our N is 140, our R is 5. So let's continue reading the question. Assume 10 of the chips do not conform to customer servers. So this is an additional thing to know when we are solving the question. There are 10 of these 140 chips does not conform to the customer requirements. So the first question says, how many different samples are possible? When they ask you how many different samples are possible without any specifications, and when you know that the case is combination, you right away implement the formula. And the formula, as we said, it is N choose R. So it's going to look something like this. These are the ways we can combine them all with each other. So we have a sample of 5, and we can have all of them good, or all 4 of them good and 1 bad, and as you can see here. But this is how we implement the formula right here. So we have N choose 5, and it is it's in the calculator. So get familiar with it. So the second question, the first one was fairly easy. The second one is going to be a little bit harder. So the second question says, how many samples of 5, okay, contain exactly one non-conforming? Now they are being chosen. They want you to have a sample of 5, as we have already had sample of 5, but this time no. They don't want all of these cases. They just want the second case where you have 4 good and 4 conforming and 1 non-conforming. So how do we solve a question like this? Bear in mind with me. So we know from the question that we have 140 semiconductors total. How many? I'm going to ask 2 questions now. How many conforming semiconductors we have? Well, we know we have 10 non-conforming, so we subtract 10 with 140, we get 130. So we have 130 conforming. How many conforming we need? We need 4. So we do 130, choose 4. Okay? My second question, how many non-conforming chips we have? Well, we have 10 here. How many we need? We need 1. So 10, choose 1. So it's going to look something like this, where you multiply both of the combinations with each other and you get this number right here. So 130, the number of conforming chips. Choose the number of conforming chips you need. Where 10, the number of non-conforming chips, choosing the number of non-conforming chips you need, which is we just need 1. In the third question, it tells us how many sample of 5 contains 3 non-conforming. Now we're playing with the numbers, same idea, but just playing with the numbers. So it's going to be quite the same idea. However, it's going to be the different case where we have 2 conforming and 2 non-conforming. Okay, 2 conforming, 2 non-conforming. How many conforming we need? 2. How many conforming we have? 130. It's the same number, nothing changed. So it's going to be 130, choose 2. Now, how many non-conforming we need? We need 3, shows there, 3. How many we have? We have 10 in the sample. So we're going to do something like this, where 130, choose 2, and 10, choose 3, and you're going to multiply them with each other, you get this number at the end. Now, let's get to the little bit more complex problem here. This problem says, how many samples of 5 contain at least 1? It did not say 1. It did not say 2. It said at least 1. So what we understand from at least 1 non-conforming chip, that it wants 1 or more. Either I get 1 chip or more. So the cases that are included in this question are these cases there. These cases there, where we have 1 non-conforming or more 1 non-conforming. So from the way we have solved the previous questions, one might hint out that, okay, I can find the combination for each one of these and add them together and I get the answer. And this is absolutely correct, but we don't want to do this. This is too much work, and you're going to do about 10 combinations and you're going to add them together. It's unnecessary. So the thing we're going to do something quite clever. As we can see from all the possible combinations that we can do, there is only one missing in this case, which is the case where we have all of them to be conforming. So does it make sense that if we get all the possible combinations and we subtract the one we don't want from them, are we going to get this one above? Yes, indeed, we're gonna get this one. So if we look back here, you can see that we have the exact same combination that we want, except for the one above, but we have already found the answer for this one. So we can use the answer for this one, then we subtract the answer for the one above, and then you get the answer that you want. So let's do it here. So as we said, we want to subtract the one below. So we get the one below, the number of combinations for the one below, and we implement this formula here, where you take all the possible combinations and you subtract what you don't want or what you don't need. In this case, the only case that we don't need in this question is where they're all conforming. So we do this and we get this answer here, which is the answer for this question. Now let's talk about permutation, the brother for combination, the one that people often confuse them together and confuse their uses together. The permutation is a unique sequence of distinct items, unique and distinct items. Here order matters. Let's take an example for this. and previously we saw the example of the candy, where, you know, if you choose the first candy and the second candy before, it doesn't matter. But here you might take an example, let's say, for example, books. You want to arrange books on the shelves, and you have 4 books. Let's say you have math, physics, chemistry, and history book. So in this case, arranging the history book before the math book or the math book before the history book is a totally different outcome. Something that should be taken into account when you are counting the number of outcomes you have. So in this case, we use permutation to find the number of ways we can arrange these books, because they are all distinct, they are all unique, and they have different sequences if you flip them together or if you switch one's place with the other. So we have 3 formulas for them. The first formula is the permutation of all items. So as we said, we have 4 books. Let's say we want to find the permutation for them, the ways we can combine them, we can arrange them on the shelf. We're going to use this formula, which is n factorial, the number of items factorial. So in the case of the books, it's going to be 4 factorial. Now, a subset permutation, which is another formula, where R is the number of items, okay, R, we remember this from combination, and N is the number of items or set we're choosing from, or locations also. So this reminds us of the combination, and also kind of have the same, it looks very similar to the formula for the combination. Here is many people also confuses it, so where they use the permutation instead of the formula for the permutation instead of the combination. We're gonna talk thoroughly, inshallah, about all the 3 formulas that we're gonna have. But this one has kind of the same job of the combination formula. However, we use this one with distinct items. So, moving to the third and last one, the permutation of some identical items. Let's say in the case of the books, we said that we have math, chemistry, physics, and history book. Let's say now we added a new history book. So now we have 5 books, but we have 2 identical books. Do we count the new history book as a distinct, unique book by itself? No, we don't do that. In this case, we use this formula, where we take the number of permutation here, but we put the number of distinct items we have. So in this case, we have now 5 books, so we put 5 factorial, and we have 2 similar books, so we have 2 factorial below. So we're gonna see how can we implement all of these formulas, inshallah. I'm not gonna redo the shot. I have redone it a lot. Now let's solve questions on permutation. So we have 3 questions. We want to cover all the cases and all the formulas we have. We're not going to cover all the cases, but at least get a good idea on what we are expecting to find in permutation questions. So the first question says, a manufacturing process consists of 10 operations that can be completed in any order. So there is order, but it can be completed in any order. So we don't have any restriction on the order, but we know that order matters in this case, because maybe the operations are distinct, are different from each other. So how many different production sequences are possible? For this question, we have to find just the permutation. We have no identical items. We have no bag that we are choosing from, or locations that we have to put or we have to care about. So we're just finding the number of possible sequences and operations. And as we have seen in this slide, the permutation for all items we have is n factorial. So we're going to use the formula n factorial, where n it equals 10, the number of operations here, and we're going to get this number at the end. Now let's move to the other question, which is another case. The question says, in a sheet metal operation, 3 notches and 4 bends are required. So we have a metal operation, and there are 7 operations that should be done, 3 notches and 4 bends, whatever this means. If the operations can be done in any order, okay, so there is order in this case, how many different ways of completing the manufacturing are possible? Okay, so it wants also the number of permutation, or the number of ways we can do this sheet metal operation in. However, there is a catch here. It told us there are 3 notches and 4 bends. So the notches and the bends are identical. Like the notches, there are 3 notches that are identical to each other, and there are 4 bends that are identical to each other. Here is the thing. You might face some difficulty figuring out what is identical, what is not identical, where it wants order, where it does not want order. You have to solve questions from the book. You need to solve questions from the book to get a grasp on what the book means and what you have to do in the questions. So ask your instructor, go to the office hours and get more practice, because this is the only way you're going to get better at this. So we understand that there are identical items here, and we said we have a formula for when we have identical items and we have order at the same time. So the formula is, the implementation of the formula is going to look like this, where we combine all the possible operations, which are the 3 notches and 4 bends equal to 7 factorial here. And we exclude, or we divide by the number of identicals we have, which we have 3 identicals, 3 factorial, and 4 identical bends, which is 4 factorial. Here we're gonna end up with this number. Last question, which is gonna be quite long. In a layout of printed circuit board for an electronic product, 12 different locations can accommodate chips. Remember, well, locations, we may want to use the second formula here. Let's read the questions. Well, here it tells you if 5 different types of chips to be placed on the board. So we have 5 different types of chips. We have 12 locations. So, and we have to understand that the chips are identical. Here's the thing. Okay, the book, it's not clear that the chips are identical. But in this case, it's not clear that the chips are different and unique. But in this case, you have to account that they are different and unique. Yeah, it do be like that. You need to practice so you can get a feel for it, or you can understand all the possible cases the book might pull through. But anyway, we said there are 5 different types of chips that to be placed on the board. How many different layouts are possible? So in this case, we're going to use the second formula, where we have the number of locations, or the number of the set, and the number of items that we have to place in the set. The implementation of it is going to look like this, where n equals to 12, the different number of locations, and r equals the number of chips that we're going to place in these locations. And we're going to implement this formula, and we're going to end up with something looks like this. Let's go to the quite difficult question here. Actually, it's not that quite difficult, but anyway. The question says, in the laboratory analysis for a sample from a chemical process, there are stories. Well, anyway, in the laboratory analysis for a sample from a chemical process, 5 samples in the process analyzed daily. In addition, a control sample is analyzed twice a day. Okay. To check the calibration of the laboratory instruments. Of course, we are going to have a story, and even the questions are stories themselves. So how many different sequences of process and control samples are possible each day? Assume that the 5 processes samples are considered to be identical. Okay, gave us an information here that the 5 processes here that we have read about here are identical. Okay. And the 2 control samples are also considered identical. So we're dealing with, in the case where we have some identical items in our permutation. So we're gonna use the last formula, where we have the formula that has some identical. So we're gonna have the total number of operations, or the number of samples being taken, which is 5. Well, here it tells us that a control sample is analyzed twice a day, so we would count it as 2, because it includes the number of operations taken a day. So we count it as 2, and then we added the 5 samples from the process, and then we divide it by the number of identicals we have, which is the lamp samples have 5 identicals, and the control samples has 2 identicals, and we're going to end up with this number. Now let's do the second question. The second question says, how many different sequences of process and control samples are possible if we consider 5 process samples to be different? Okay, so the 5 samples, the 5 lab samples that we had here, now they are considering them to be different, not identical. Okay, let's continue reading. And the 2 control samples to be identical. So the control samples are still identical, but the lab samples, now they are considering them to be different. So how do we solve this question? Well, we have the lab samples now to be different and the control samples to be identical. We can solve it with the exact same formula. Now, this time, we don't consider the lab samples to be identical, and we get something that looks like this. Still, we are doing 7 operations. However, this time, we only have 2 identicals, and the rest are just different. Good. Now, the last question. For the same situation as part B, how many sequences are possible if the first test of each day must be controlled sample? Okay. So it told us here that the first, for the same situation as in part B. So it means this, that the lab sample 5 are different and the control samples are 2 identical. However, it told us that how many sequences are possible if the first test each day must be control sample. So we know for a fact that the first test each day is from the control sample. So the rest that we're going to end up with, if we take one of the control samples, we're going to end up with 1 control sample. That's it. So our new data going to be, the lab samples 5 are different. I forgot to color it with red. And the control sample now is 1 because the first one is already gone. We did it. It's already done. We don't care about it. خلاص, it's a done deal. It's the first thing we do every day. We don't need to account for it anymore. So the control sample is now just 1. So we can implement the formula like this, where now we have 6 operations that we do, and we don't have pretty much any similarity, but I have kept it like this so it become clear. So that's it for permutation questions. In the previous semester, when I was taking course ISE 205, in chapter 2, my instructor brought a password question in the quiz. And because it's a fertile ground for trick questions, and you can make all sorts of questions. You can pull out 100 questions from just a password question. So I wanted to solve one to make it clear and give an idea for students on how to solve these sorts of questions. It's going to come often as a story, so buckle up. So the question says, a computer system uses passwords, okay, that contains exactly 8 characters. Okay, keep in mind we have 8 characters because the number of characters is important. So in each character, you can use one of 26 lowercase letters, okay, or 26 uppercase letters, nothing strange, or 10 integers from 0 to 9, okay. Now they are going to define events. Let alpha denote the set of all possible passwords. Let A and B denote the events that consist of passwords with only letters and integers respectively. So the event of A is a password that only consists of letters, and B is a password that only consists of integers. So determine the number of passwords in each of the following events. So let's start with the first event, event alpha. So event alpha said denote all the possible passwords. Okay, so let's have this shape here. This is going to help us tremendously in solving these questions. So this denotes the number of 8 characters. So we said we have 8 characters, so we have 8 slots that we can put the characters in. So let's start solving. In this first slot, how many possible characters can I put inside of them? How many possible characters can I choose from? So let's reread the question. Well, it says here we can choose one of 26 lowercase letters, and one of 26 uppercase letters, and one of 10 integers. So 26 and 26, that's 52, plus 10, that's 62. So I can choose one of 62 possible characters in this slot here. What about the second slot? It's the same case. There is no any condition tells you that you cannot put the same letter here or nothing of this sort. So you can put the same number of characters in this slot as you can put in this, as you can put in this, as you can put in this, and all of them. So let's put the number of characters that we can put in each slot here. Okay? Now, what does this remind us of? It is multiplication rule, where we have multiple steps, and each step has number of options. So to find the number of outcomes for this event here, we have to multiply them all with each other, each option from the other step, and we multiply them all together, and we're going to end up with this number, 62 to the power 8. This is the answer for question A. Question A, yes, which is omega. Did I say alpha? It is omega. Anyway, question B wants to find event A. An event A says it is the event that consists of password with only letters. Okay, so in this case we have a different thing here because we're not allowed to use everything in the password. We're only allowed to use letters. So let's put our grid, or whatever you want to call it, our table here, our slots where we can plug in our characters. Now we can only put letters in these slots. So how many letters can we put? So we have 26 lowercase letters and 26 uppercase letters. So 26 and 26, this is 52. So we can put 52 in each one of these slots. So 52, and you multiply them all with each other because it's still the multiplication rule. You're gonna get 52 to the power 8. Now we have this question that looks so weird. Like, even if you would try to understand it, it would be quite confusing. How to solve it? Well, remember De Morgan's rule. When you have something weird like this, you can make it into something less weird that looks like this, where you only need to find the union between A and B, and then get the prime of them instead of doing this. I don't know what is this. So let's try to do it. Let's put our slots here. So if we do a union between A and B, well, A takes all the letters and B denotes all the integers. So if we take the letters and integers and we combine them together, how many outcomes we have? We have all 62 possible outcomes. However, take the prime of them, take the complement of them. You're not going to end up with anything, because if you don't use letters or you don't use integers in your password, you're literally not going to end up with anything. So this is an empty set where we only have 0. So the answer for this question is 5. I forgot to put 5. Now we have solved 3 of the 5 questions. Now let's continue solving the 2, which are a little bit more complicated. Needs more thought, but they are still easy. This question is the one that I gotten wrong in the quiz. So yeah, let's solve it here. Well, the password that contains exactly one integer. So let's put our slot here. It tells us that only contains one integer. So let's put our one integer in this slot to begin with. Okay, we put it in this slot. So how many integers can I choose from? From 0 to 9, we have 10. So I can choose 10 integers, and the rest are going to be letters because it told me exactly one integer. If I put 2, then it's wrong. I'll only need one integer. So the rest are going to be letters. So we're going to have something that looks like this, where the first one is just integers and the rest are just letters. Here is what I got wrong. I just did this, and I did the multiplication rule, and I put the answer as it is. Here's the thing. What if we want to put the integer here? What if we want to put it here? What if we want to put it here, or here, or here, or any other slot here? We have 8 slots. We only accounted for where we have the integer in the first slot only. We need to account for the 8 slots, all of them. So we have to multiply this with all the possible slots it can be in, which are 8. So if we're gonna solve it, we're gonna take the multiplication rule, multiply all of these together, and then multiply with 8, which are the number of possible places the integer can be in. So this was my mistake. This 8 was my mistake in the quiz. Now let's solve the last question, where it tells us that they want all the possible outcomes for passwords that contains at least one integer. We remember hearing the word at least, which means either if it told us at least one integer, so it wants either one or more than one integer in our passwords. So it wants to know the number of combinations we can use for having at least one integer in our password, or more than one integer, maybe 2 integers, 3, 4, 5, up to 8, because we have 8 slots. We remember how we solved it. We used this formula right here, which is taking all the possibilities and we subtract the unwanted possibility from it. What is the unwanted possibility in this case? Well, we have when we have at least one integer, it includes one integer, 2, 3, 4, 5, 6, 7, 8. What about no integers? The case that is unwanted in this case, where we don't have any integers in our password. And when we don't have any integers in our password, what do we have? We have letters. And the case for letters have been already solved. We already solved it in the previous example here, which is the case. I think it's this one. Yes, which is the case of event A. Question B. Event A has only letters in it. So we know the number of outcomes here, which is 52 raised to power 8. So we can take it and we can implement it in this question. And the number of possibilities also, we found it. Okay, I should get back. Which is the omega in this case. You see, the omega is all the possible value, all the possible combination as it's defined, denotes all the possible passwords. And A is the unwanted ones, the ones that only has letters. So we subtract them from each other and we get our answer for the question. I did not solve it because I did not put the number because I think the calculator gonna die or something. So yeah, this is it for the password questions. Now let's talk about probability, the title of the chapter. Well, it is the thing. It's from now on we're gonna be dealing mostly with probabilities. So we're going to be asked to find probabilities of stuff and we're going to find likelihood of stuff. So we have to familiarize ourselves well with what probability is and take a good foundation and we build a good foundation for how do we deal with probability. So what is probability to begin with? It is the likelihood or a chance that a particular outcome or event from a random experiment will occur. So we remember our tossing a coin once example. And we have our sample space to be either a head or a tail. So what is a numeric representation for the chance of either the head or the tail happening? We call it a probability. And in this case, it's going to be 0.5 or 50% chance of either one of them occurring. So probability, first of all, is a number. It's a numeric representation of the likelihood or the chance. It is between 0 and 1 inclusive, so it can be 0 and it also can be 1 or anything between them. However, it can't be more than 1, it cannot be less than 0. This is completely wrong. If you're in an exam or in a quiz and you got something that is different than this condition here, it's definitely 0. It's definitely wrong. I mean, not 0. 0 in the mark. Anyway. 1 means certainty. So if you got 1, it's impossible that the event will not occur. So it will definitely occur. And 0 means impossibility, that impossible for the event to occur at all. And we denote the probability by having the letter P, and we have the event, the denotation for the event inside of the bracket. So whether the event was event probability of A, probability of B, probability of E1, it's just a denotation. The book. So the question says the sample space of a random experiment is A, B, C, D, and E with probabilities, the list of probabilities respectively. So each one of these is respectively corresponding to one of these probabilities. So A to the first one, B to the second one, and so on. So let A, our first event, let A denote the event A, B, and C. So it includes A and B and C from the sample space. And let B denote the event C, D, and E from the sample space also. So let's solve these questions here for them. First, let's find the probability of A. The probability of A, as we can see, includes A and B and C. And the likelihood for A is 0.1, as it's arranged here, as we can see. And B is second one, which is 0.1. And C, the third one, to be 0.2. So if we add all of this probability, we're going to find the probability for A, which is sums up to 0.4. Now, probability of B. So let's be denoted by the event C, D, and E. So C, D, and E, the last three ones we have 0.1, 0.4, and 0.2. So if we add them together, we're going to get 0.8. Extremely simple. Now, let's find the complement of A. So the complement of A is 1 minus the probability of A. So 1 minus the probability of A here is going to result in 0.6. Let's go to this one. The probability of A union B. So if we add the probability of, if we add A union B, A has A, B, and C. And B has C, D, and E. So with this we have A, B, C, D, E. So we have all the letters in the sample space. Therefore, this equals our sample space, and the probability of the sample space is always 1. Now, let's take the last one, the last question here, which wants the intersection or the common event or the common outcome inside of event A and event B. So the common outcome here is, as we can see here, we have C and we have C in both cases. So If we find the probability of C, it's going to be 0.2. And that's it. That's merely it. Extremely simple. Now let's talk about the axioms of probability. There are some axioms that we have to understand before, so we can use their properties in our benefit, to our benefit. So if S is the sample space and E is the event from the sample space, then probability of S is always 1, as we have seen, and the probability of the event is always from 0 to 1 included. So it can be 0 and it can be 1, but it is also always in between. But it's always within this range. It cannot be more than 1. It can never be less than 0. For any two events, E1 and E2, with the intersection equals empty set, then the union of them is the addition probability of both of them. Let me explain this furthermore. So if we have mutually exclusive events, the ones that we have seen in the Venn diagram, the one where you don't have no commonalities at all between the events, the union of them is basically adding the probabilities of both of them, because if they had intersection, we're gonna have a totally different formula for this. So if they have no commonalities at all, the union of them is gonna be just adding the probabilities of them. That's it. And lastly, the complement of an event, the probability of the complement of an event is 1 minus the probability of the event. You can see it here. It's written better than I explained it. Now let's go to the addition rule. Here I told you that this only works if we have this case there. Now let's explain why it is like this. Why can't we do it to all the probabilities? Because we have this formula to account for the general events where they have intersections and stuff, and this one for when they don't have intersections. We call them mutually exclusive. Now let's see if we do this formula for two events that have intersection between them. Let's see. So at the beginning we're gonna add a probability of B. For example, we're gonna add probability of B. Okay, nothing wrong. And then we add it to the probability of A. So if we add them, we're gonna have this area added twice. We're gonna add this area twice, and we're gonna have totally different answer. So we have to subtract this area so we can get the additional probability of these two instead of this area twice and these two together. So what we do is we add one of the areas, and then we subtract the area in the middle here, the intersection between them, we subtract it. Of course, as I've said, this only works for the case, this is incorrect, and this only works for the case where we have mutually exclusive events like this. So if we add them, there is no intersection, nobody's gonna say anything. Now let's solve some questions about the addition rule. So we have these questions here, and we have some probabilities that we are given, and we need to solve questions with the given probability. So let's start. The first question, extremely easy. Probability of A complement. Well, the probability of A complement equals to 1 minus the probability of A. So we're going to end up with 0.7. This is A, 1 minus it's going to be 0.7. So probability of A union B. Here is the catch. We have an intersection here. So they are not mutually exclusive. They have some common ground between them. So we have to add these probabilities, and we need to subtract the common ground between them, and we're gonna end up with this. This question and this question, I'm not really familiar with them. They use something called the total probability rule, which is something we have not taken yet. But if you want to solve them, that they are solved by this way. I think that's what I found. If it was not incorrect, I'm gonna write down in the comments. So question E. Question which asks for the probability of the union of A and B complement. We have already found the union between A and B. We just have to subtract it by 1, and we're gonna get 0.6. The last one, probability of A prime union B, it's gonna go with the same condition, where we're gonna have the probability of A plus probability of B minus the intersection here, which is the one that requires total probability rule. So if you found this one, you can find this one easily, with the same formula. Now let's talk about conditional probability. the conditional probability of an event A given that event B already happened. So conditional probability asks you for the event with the condition that there is another event that have already happened. So in this case, this is going to be denoted by this, and this is the formula of how can you find it. So if the probability of A given this boundary is given, so remember our complement and union and intersection have words that will infer to them, like union have or, and intersection has the word and complement has not. Given conditional probability has the word given. So if you see it, there may be an indicator that you have a conditional probability here. So you read this by probability of A given B, given, which means that this one that already happened. So this is the formula, finding the intersection, and you divide it by the probability of the given event. So the complement of conditional probability, which is a thing you have to focus on, because in coming questions, you will have to find the complement, and if you found it incorrectly, you're going to solve the entire question incorrectly. And we got a question that we had to find the complement for in the major exam. So the way to find the complement for the conditional probability is like this, where you take 1 minus the complement of the first event. If you do something like this, totally incorrect. If you do something like this, also incorrect. This is now not how you take the complement of the conditional probability. So bear in mind, this is the correct way. Now let's solve some questions on conditional probability. The questions, some of the questions come as tables. So I wanted to solve one of the table questions. So how to solve the table questions? Well, first of all, you have to find the events that are denoted in the question. So the events are denoted here to be the event that a sample has low melanin content, and B denotes the event that has a sample of high moisture content. So here we have melanin content, we have moisture content, high, low, high, and low. A, we said, denotes the low melanin, so it takes into consideration this, and B denotes the sample where I have high moisture, which is this here. Yes, this here. I like to do this. I like to do this in the table, so I can sum these numbers and I get definite numbers. So when someone asks me how many people have high moisture content, I don't sum the 13 with the 7. I just have the numbers already ready for me, like here. So we have 20, the number of people who have high moisture content. The number of people who have low moisture content are 80, and melanin content and low melanin content. And if you add them here, if you add these, you have to end up with the same number as if you add these. That's a way to make sure. Now let's solve the questions. So we have these questions on the on the table. So we have to find the probability of event A. What is event A? Which is the event that the sample has low melanin content. So where is the low melanin content? So these are the low melanin contents. So we have to take the number of the samples that has low melanin content, and we divide it by the total number of samples. Where is the total number of samples? It's this one here. After we add them together, we're gonna get this number here. And we divide it by what? By this number here, which is the number of people who have low melanin content, and we're gonna end up with 39/100. Now, probability of B is denoted to be the sample of high moisture content. So we have high moisture content, we add these numbers, we're gonna get the 20, then we divide the 20 over the total number of probability we have, the total number of samples we have, or the observations we have. So it's gonna end up something like this. Now we're gonna need the conditional probability because we're gonna solve these questions. So the question says, find the probability of event A, which is low melanin content, given we have a person who is also at the same time has a high moisture content. So how to solve it? Implement the formula right away. So find the intersection between event A and B. Event A, low melanin content. Event B, high moisture content. So high moisture content, low melanin content. This is the intersection between them, number 7. So we're gonna have number 7 here up top. Then we're gonna have the probability of event B. What is event B here? High moisture content again. So high moisture content is 20. So we're gonna have 7 over 20. This is how to solve section C. Now let's go to D. Same idea, there is nothing different. You're gonna take B, which is our event, and the given event, the condition is event A. So we're gonna find first of all the intersection. Well, the intersection between A and B we have already found it, which is number 7. But this time we're not gonna divide over B. We're gonna divide over A. So if we find A, the total number of A event observations, which is for the low melanin content, which is gonna be 39. So it's gonna be 7 over 39. Okay. So now let's have some practice on the conditional let's have more practice on the conditional probability. So let's say we have this question. A batch of 50 parts contains 10 made by tool 1 and 40 made by tool 2. If 2 parts are selected randomly, here is a visual aid for the parts where the parts made by tool 2 is in blue and by tool 1 made in red. Well, we have the question to state that what is the probability that second part came from tool 1 given that the first part came already from tool 1? Well, we know with this given here that is a conditional probability where this event have already taken place, and now we're asked to find the probability of this event while knowing that this event already took place. So the first event, that the one that already took place, given that the first part came from tool 1, we know that there is a part in our batch that has been already taken. So we can, well, given of course conditional, but so we can discard it, we can ignore it. So now our batch, instead of having 50, now it has 49. So with this, we can state here the probabilities for each tool, or for each tool, or for each tool. So if you take a part from tool 1, the first part being from tool 1, you're gonna have probability of the number of parts from tool 1 over the total number of parts in the batch, which is 40 over 50, and the same goes for tool 2, 10 over 50. However, in this case, we're not finding this, but we are finding this long probability here, which is the second part from tool 1 given that the first part from tool 2. And we know that we have already discarded the tool was taken by tool 1. So we are remained with 49, and the number of tools made by tool 2 have not changed. So we have 40 over 49. Second question states that what is the probability that the first part came from tool 1 and the second part came from tool 2? So the and here, as we have seen before, means intersection. So we want to find the intersection between first part coming from tool 1 and the second part coming from tool 2. And it stated something like this. And if we want to find the intersection of events that are independent of each other, the one that we assuming here, we're gonna talk more about independence, but we are assuming that we're gonna have independent events unless we are told that they are dependent, or we have to find the dependency for them. However, we assume that these are independent. So if we have intersection of two independent events, solving the intersection for them is multiplying the probability of these two events. So the probability of the first part from tool 1, we have it here, which is 10 over 50, and the second part from tool 2 is gonna be this one, knowing that already have taken from tool 1. So it's gonna be this one here. We're gonna have 8 over 49. I should have written this in a conditional probability way, but anyway, this is the solution for the question. So now let's have more practice on conditional probability, this time about multiplication rule. So we have this question here, and I would advise, even if the question is long, I would advise that you would read the entirety of the question, then you go look for the important stuff, because there might be tricks laying somewhere hidden inside the question. So you should read the entirety first, then you go we go solving. We're gonna do it right now. So the probability that the first stage of a numerically controlled machine operation of high RPM meets the specification is 0.9. Okay. Failure due to meter variation, fixture alignment, cutting blade condition, vibration, and ambient environment conditions. Given, okay, that the first stage meets specification, the probability that the second stage meeting of machining meet specification is 0.95. It's the probability that both stages meet specification. Okay, so let's note our events first. So the first number we have here is 0.9. Let's go to it and see what it means. So the probability of the first stage of numerically controlled machine operation meets specification. So the entirety of this is not really important except for the part where it says the first stage and it meets specification. So the first stage of this operation meeting specification, this is the probability for it. So we can denote our first event as A, where it denotes that the first stage meets specification. And the probability for it, for A, is 0.9. Now, let's go to the second number we have here. It said, given that the first stage, okay, so the first stage is a given. It's a conditional probability. Given that the first stage meets specification, the probability for the second stage of machining meets specification is this one. So we have our second event, which is that the second stage meets specification, but we don't have the probability of the second stage meeting specification. We have the probability of the second stage meeting specification given that the first stage have already met specification. So it's going to look something like this. Saying so much words is kind of confusing, but get what you want from the question and that's it. So this is what it means. What's asking us from the question is to find the probability of both stages meeting specifications. So we need the intersection of both of these stages. So probability of A and B being both meeting specification or both successful at the same time. So we're gonna implement this formula simply and we're gonna get this answer in return. So let's talk about total probability rule. Total probability rule is very useful in finding some probabilities for certain events that we don't necessarily know, but we know an information about them, like the intersection with other events. So let's have this picture here to demonstrate the total probability rule in a better way. So let's say that we have event 1, 2, and 3, and 4, all mutually exclusive. So event 1 and 2 has no intersections between each other, and the same goes for the rest of the events here. And let's say that we have an event B that is inside and contained in all of these events. So as we can see here from the formula, the probability of the intersection of each event of these, E1, 2, and up to 4, with event B, if you sum the probabilities of them all, you're going to get event B at the end. And we have here modified it or harnessed it so we can solve questions regarding conditional probability, as we're going to see. Let's solve a question on total probability now. So let's say that we have this question. The question says, in a particular production run, 20% of the chips subjected to high levels of contamination, 30% subjected to medium levels of contamination, and 50% subjected to low levels of contamination. What is the probability that a product using one of these chips fail? So the probability of a product using one of these chips, so it wants the probability of failure of these chips. So if they fail, the product fails. So in simple terms, they just want to know the probability of failure for the chips. Now the question looks like a handful and you don't know really from where to tackle it. But we're going to dissect it bit by bit, part by part, and we're going to see how can we solve it easily and use the formula in our advantage. So let me do a separation. First of all, identify what they want from you. What they want from you is the probability that a product using one of these chips fails. So the probability of failure for the chips. I'm going to denote it by the letter F. So I'm going to denote the failure by the letter F. Now I'm going to put the formula because we are going, okay, probability of F is the thing we want. Now I'm going to put the formula to see how can we use it and what do we need to find from this question so we can use this formula to solve the question. So let's reread the question and let's see what these numbers mean here. So in a particular production run, 20% of the chips are subjected to high levels of contamination. So we have an information about what is the probability or the proportion of our chips that has a high level of contamination. I'm going to denote this by the letter H. So the chips that are exposed to high levels of contamination denoted by H. What's the probability of this? This 20%. So it's going to be 0.2. Now, let's continue. We have other numbers we can use in this question. So let's go to the other one, 30% to medium levels of contamination. So we know for a fact that the proportion of the chips that has a medium level of contamination is 30%. So I'm going to denote it by the letter M, and this is the probability for it, which is 0.3, 30%. Naturally, the last one is going to be the same exact process, 50% to low levels of contamination. So I'm going to denote it by the letter L, and the probability for it is 50% or 0.5. Now, we have finished with the numbers here in the question. Let's go to the table. What does the table mean? Like, if you're looking at it for the first time, you can't really know how can you use it to find the answers that you want. Now, let's look at the formula for a bit. The formula says we want to find the probability of B. In this case, is the probability of F. So we want, let's say that we substitute it here with F. So let's say that we want to find the probability of F given each and every mutually exclusive event that has the probability of F in it. So in this case, this is demonstrated with the table here. So the table has the probability of failure given the level of contamination. So as it shows here, it's corresponding. Each level of failure corresponds to a level of contamination. So our first level, so the first level of contamination and the probability of failure for it is this one here, which is 0.1 with the high level of contamination. So we can denote it as the probability of failure given the high level of contamination. And the same goes for the rest. As we can see, 0.01 for medium. So it's the level of failure given that we know that the chip has a medium level of contamination. And the last one goes for the low, and it's straightforward. Now, we have everything we need to solve the question. Let's solve it. Let's just plug in numbers. So it is probability of high multiplied by the probability of failure given high. Then we add to it the probability of medium multiplied by the probability of failure for the medium, and it shows here better than saying it. So we can just plug in the numbers here, and we're gonna inshallah end up with this number there. So this is it for the total probability. For this example for total probability. Now let's solve another question about the same idea. It's going to be long, but I would recommend that you read it at its entirety, because if there was going to be a trick in the question, you're going to be aware of it. So let's read it. The edge roughness of a slit paper product increase as knife blades wear. Okay, this is logical. Only 1% of products slit with new blades have rough edges. Okay. 3% of products slit with blades of average sharpness exhibit roughness, and 5% of products with slit with worn blades exhibit roughness. Okay, if 25% of blades in manufacturing are new, okay, we've heard new in the question here, 1% of product with new blades, so this is something to keep in mind. 60% are of average sharpness. Also, we heard average in this part of the question, so also keep it in mind. Of course, it's all going to be linked, but I'm trying to point out that you have to look out for the familiarities in these questions because it's going to be long, and having a methodology or a method that you can dissect the question in a better way is going to be way beneficial for you if it's in an exam setting. Let's continue reading. And 15% are worn. Of course, we saw the word worn here. So what is the proportion of products that exhibit edge roughness? Now, at this end part of the question, we know what they want from us. They want the proportion of products that exhibit edge roughness. So I'm going to denote this event by R. So R denotes roughness. And the probability, which is the proportion, is the number that we want to find in this case. So let's take it bit by bit. Now let's gonna dissect the rest of the question. So here is a thing that I do in these sorts of questions. Sometimes, not always, sometimes you can see a part of the question where all the probabilities sum to 100. This can be useful. as long as you know what you are doing, this can be useful for you, because they can be the events that you're going to be multiplying the conditional events with. Let's see. So here we know that 20% of the blades in manufacturing are new. So the proportion of the blades in our manufacturing process that are new is 25%. I'm going to denote this event by I think n, that I have denoted it by n. Yes, I denoted it by n. And the 60% of average sharpness is going to be the 60% of blades that have average sharpness. I'm going to denote this by A. Of course, the probability for this is 25%, which is 0.25, and this is going to be denoted by A, and it's going to have a probability of 60%, which is 0.6. And at the end, we're going to have the worn edges, which make about 15% of our batch. So we have the events, the probability for the events now. Now let's look for the conditional events. Let's get back to these probabilities up here. So here it tells you only 1% of products slit with new blades have rough edges. So what we understand from this number, this number demonstrates, or this number is for the probability of roughness, given that we know that the blade is new. So we can denote it like this: the probability of roughness, knowing that, or given that the blade that we are observing is new. So this is the probability for it. Let's go for the other number, which is 3%. 3% of the products slit with blades of average sharpness exhibit roughness. Okay, so this is the probability for the roughness, given that we know that the blades of average sharpness. So we can put it here because, of course, we're going to use it to solve the question. And the last probability here we have, which is the 5% of product slit with worn blades exhibit roughness. So naturally, this is going to be the probability of roughness, given that we know that the blade is worn. So we're going to put it here. And with all of this, we can just plug in the numbers in the formula, and we get the answer simply to be this one. Take a look at this, and take a look at this, and take a better look at this question. I believe that if you observe the questions more, you're going to get a better understanding than someone explaining them to you. So get a feeling for them, because these questions are often long. So you need to get a feeling for them more than finding the logic behind them, which is going to be good also. So if you find the logic behind them. So let's continue. Now, let's talk about independence. Independence is the fact that one event A, let's denote it as event A, has no impact at all on the probability of another event B. So if they are independent, they have nothing to do with each other. If A happened, B is out of the picture. So independence is a clear concept. But we have here some formulas to make sure that the data we have is independent from each other. Using either one of them is going to be okay. If you use one of them and you get the answer, you don't need to use the rest. So if these formulas are correct, then you are going to end up with independent. But if you get maybe this side not equal to this side, then your data is dependent on each other. Using one of these formulas in the VOC, of course, as I have mentioned. Now, independence of multiple events. So if we have a combination of events, we have event 1, event 2, up to event k, are independent if and only if, for any subset of these events, the intersection of each one of these events, the probability of the intersection of all of these events is simply the multiplication of all of these events combined. So in simple terms, if you have independent events and you want to find the intersection between them, just multiply the probability between them all, and that's it. We're going to see an example for this, extremely simple example. Now let's have a question on independence. Let's say that we have this question here. The question says that the probability that a wafer contains a large particle of contamination is 0.01. So this number denotes the probability that our wafer has contamination in simple terms. So I'm going to denote this event with the letter E, and the probability for this event that the wafer has contamination is 0.01. Let's continue reading the question. and that the wafers are independent. So we can use the formula that we have seen earlier about independence. Okay, that is the probability that a wafer contains a large particle does not depend on the characteristic of any other wafers. He's just explaining what independence is. So you can omit this this argument here, or this this sentence here. If 15 wafers are analyzed, so we have to analyze 15 wafers at this time, where the independence is going to come in handy. So what is the probability that no large particles are found? Here is a thing that you have to pay attention to. Here, he wants the probability of no large particle are found, so the probability of no contamination. So how can we find the probability of no contamination in this case? We take the complement of event E. So the complement of event E, which is the event of no contamination, is going to be 0.99. Are we done? No, we're not done. We want to find the probability of 15 wafers being analyzed and all of them at the same simultaneous event not have contamination. So how are we going to solve it? We just simply have to multiply each and every one probability of these chips or wafers having contamination with the other. Simply, we're going to end up with something that look like this, which is the probability of 15 particles not having contamination. Extremely simple. Now let's solve a question about independence. The question says, parallel circuits. The following circuit operates only if there is a path of functional devices from left to right. So this is our left side and this is our right side. And the circuit only operates if the current moves from this side to this side. And it has to pass through devices. The probability that each device functioning is shown in the graph. So this number here denotes or defines the probability of each of these devices actually functioning. If they fail, the current cannot pass. So this is the probability of them functioning. Now, assume that the devices fail independently. So here we have an information that they are independent. We may be able to use the rules of independence here. So what is the probability that the circuit operates? So we know that for the circle or for the circuit to operate, the current have to move from the left to the right side. However, here we have two paths. It can go through this device or this device. So either one of these devices working is gonna be good. So we want either one of them or both of them to work. It's you know, it does not matter. We want one of them to work. So what we want to find here is the probability that of the bottom device or the top device succeeding and working. So how can we find it? Well, first of all, we have to define our events. So the first event, T, denotes that the top device succeeds, which is this one succeeding. And B denotes that the bottom device succeeds, which is this one below here. So now it's gonna show the entire solution, but I'm going to talk over it. I'm gonna explain how did we reach the conclusion. So the solution shows in here. So we know that we want either the top device or the bottom device to work. So we're gonna have the probability of T, which is the top device succeeding, union the probability of B, the bottom device succeeding. So to solve we have a problem here though. The rule or the formulas that we got for independence are for intersection, not for union. We have a union here. It can't work on union. So we have to manipulate the formula or we have to manipulate the formulas here. So we can get it to a point where we have intersection, so we can use the independence formula. So first of all, we got this our generic one here. Then we took the complement of it. So 1 minus the probability of T union B complement. Here it used De Morgan's law, so we can have an intersection here, as it shows in De Morgan's law. This argument can turn into this argument where we're gonna have an intersection, and when we have an intersection, we can finally use the formulas for independence, where here we can multiply the intersection of two independent events with each other, and we're gonna end up with something that looks like this, and this is gonna be the answer for our question. Hopefully it is clear. Now let's talk about Bayes' theorem. Bayes' theorem is this formula shown in here, where if you have the conditional if you want to find the conditional probability of A given B, you can find it by using the conditional probability of B given A, multiplying it by the probability of A divided by B, as it shows here clearly from the formula here. Bayes' theorem with total probability, we can use Bayes' theorem with total probability, the one that we have seen. This is the total probability, and this is the implementation of Bayes' theorem with it. So this also can be used to solve some questions. Now let's solve a question on Bayes' theorem. So the question says an email filter is planned to separate valid emails from spam. The word free occurs in 60% of the spam messages and only 4% of the valid messages. Also, 20% of the messages are spam. Determine the following probabilities, and we have here question that we have to determine the probability of each one of these questions. First of all, let's define our events. So the first visible events that we can see is the word free occurrence. So the occurrence of the word free is an event. So let's keep it there. And also we have the spam messages as an event, and the occurrence of valid messages is also an event. So we can define them like this: F, where it denotes the occurrence of the word free; S for spam messages; and V for valid messages. Now let's solve question 1. The question 1 says the message contains the word free. So we want the probability of free occurring. So we want the probability of F. Probability of F is the thing that we want to find in this question. And to find it, let's look at what these numbers might help us with in finding the probability of free. So the first number here, the first probability we have, which is the word free occur in 60% of spam messages, is the probability of the word free occurring given that we know it is a spam message. So we can say that this probability is the probability of F, given that we know it's a spam message, which is the probability of S. So it would look something like this, which is 60% or 0.6. Now continue, and only 4% of valid messages. So the word free occurs in only 4% of valid messages. So given the fact that we know that it's a valid message, the probability of it has the word free is just 4%. So we can denote it here as the probability of free, or F, given V, which is 0.04. Now, we remember that if we want to implement the formula, we have to find the probability of S and the probability of V. So the last probability we have in the question here is 20% of the messages are spam. So we know the probability of S, which is 20% or 0.2. But it did not give us the probability of V. How can we find it? Well, we know that messages are either spam or valid. So if the message that we got is not in the 20% messages that are spam, it must be in the 80% that are valid, because 80 is completing 20, and the sample space only consists of these two outcomes, which is either spam or valid. So we're going to end up with the probability of valid being 0.8. So we can implement the formula here, and if we implement the formula, we're going to get this answer, inshallah. So let's go to the other question, which is question B. The message is spam given that it contains the word free. So we want the probability of spam, which is S, given that it's free. So probability of S given F, which is going to look like this: probability of S given F. So how to solve it? Here we can use Bayes' theorem, which is this one here. What we want to solve this question, we want the probability of F given S, the probability of S, and probability of F. And we have found all of these already, so we can just plug in the numbers from the answers and the variables that we have found here, and we plug them into the formula, and we're gonna get the answers at the end, which is that number there. Now let's solve the last question, which is question C here. The message is valid given that it does not contain the word free. So here we have it contains free, and the event here, we have defined our event to contain free, but this question wants the probability that the message is valid given that it does not contain free. So how can we denote it so we can solve it? We can denote it like this. So the probability of V, which is a message being valid here, given, this is the given, that it does not contain 3, which is f prime. So how can we find it? We implement the formula also. If we implement the formula, we're going to get something that looks like this. Well, here is a problem. We only have one of the variables that we need. The rest of the two, these two, we don't have them. We don't know them. I'm going to tell you it is extremely easy to find them, but bear in with me. Here is the thing. We know the probability of f given v. Here we want the probability of f prime given b, but we have f given b. And here we want the probability of f prime, but we have the probability of f. So how can we find those from those? Here is the thing. We just need to find complements. So if we want to find them, if we want to find probability of f prime given v, we can just take the complement of the probability of f given v, and we're going to find the probability of f prime given v, which is going to be this number there. And this one is extremely easy. We know how to do it, which is also finding the complement. But bear in mind, I have mentioned earlier when I talked about the conditional probability that you have to do the conditional probability as how it should be done. Because if you mistake, maybe you put the prime on the v instead of the f, or you put the prime on them both, then you're going to get a totally different answer, and you're going to get a totally incorrect result at the end. So if you did not see how we can take the complement of conditional probabilities or conditional events, get back in the video and check it, because it's going to be extremely useful. And with this, we conclude the chapter. I apologize if I was in a hurry at the last questions, because I wanted to finish it fast so I can upload it before your majors. And with this we are done. هذا والله أعلم. قواكم الله. الله يوفق لكم في اختباراتكم. في أمان الله.